Aerospace engineering is the primary field of engineering concerned with the development of aircraft and spacecraft. It is divided into two major and overlapping branches: aeronautical engineering and astronautical engineering. Aeronautical engineering was the original term for the field. As flight technology advanced to include craft operating in outer space, the broader term aerospace engineering has largely replaced it in common usage. Aerospace engineering, particularly the astronautics branch, is often colloquially referred to as rocket science. Overview: flight vehicles are subjected to demanding conditions such as those produced by changes in atmospheric pressure and temperature, with structural loads applied upon vehicle components. Consequently, they are usually the products of various technological and engineering disciplines including aerodynamics, propulsion, avionics, materials science, structural analysis and manufacturing. The interaction between these technologies is known as aerospace engineering. Because of the complexity and number of disciplines involved, aerospace engineering is carried out by teams of engineers, each having their own specialized area of expertise. History: the origin of aerospace engineering can be traced back to the aviation pioneers around the late 19th to early 20th centuries, although the work of Sir George Cayley dates from the last decade of the 18th to mid-19th century. One of the most important people in the history of aeronautics, Cayley was a pioneer in aeronautical engineering and is credited as the first person to separate the forces of lift and drag, which are in effect on any flight vehicle. Early knowledge of aeronautical engineering was largely empirical, with some concepts and skills imported from other branches of engineering. Scientists understood some key elements of aerospace engineering, like fluid dynamics, in the 18th century. Many years later, after the successful flights by the Wright brothers, the 1910s, or the development of aeronautical engineering through the design of World War I military aircraft. The first definition of aerospace engineering appeared in February 1958. The definition considered the Earth's atmosphere and the outer space as a single realm, thereby encompassing both aircraft and spacecraft under a newly coined word, aerospace. In response to the USSR launching the first satellite, Sputnik, into space on October 4, 1957, U.S. aerospace engineers launched the first American satellite on January 31, 1958. The National Aeronautics and Space Administration was founded in 1958 as a response to the Cold War. Elements: some of the elements of aerospace engineering are radar cross-section, the study of vehicle signature apparent to radar, remote sensing; fluid mechanics, the study of fluid flow around objects, specifically aerodynamics concerning the flow of air over bodies such as wings or through objects such as wind tunnels; astrodynamics, the study of orbital mechanics including prediction of orbital elements when given of select few variables. While few schools in the United States teach this at the undergraduate level, several have graduate programs covering this topic. Statics and dynamics, the study of movement, forces, moments in mechanical systems; mathematics, in particular calculus, differential equations, and linear algebra; electrotechnology, the study of electronics within engineering; propulsion, the energy to move a vehicle through the air is provided by internal combustion engines, jet engines and turbomachinery, or rockets. A more recent addition to this module is electric propulsion and ion propulsion. Control engineering, the study of mathematical modeling of the dynamic behavior of systems and designing them, usually using feedback signals, so that the dynamic behavior is desirable. This applies to the dynamic behavior of aircraft, spacecraft, propulsion systems, and subsystems that exist on aerospace vehicles. Aircraft structures, design of the physical configuration of the craft to withstand the forces encountered during flight. Aerospace engineering aims to keep structures lightweight and low cost, while maintaining structural integrity. Materials science, related to structures. Aerospace engineering also studies the materials of which the aerospace structures are to be built. New materials with very specific properties are invented, or existing ones are modified to improve the performance. Solid mechanics, closely related to material science, is solid mechanics, which deals with stress and strain analysis of the components of the vehicle. Nowadays there are several finite element programs such as MSc Patron and Astron which aid engineers in the analytical process. Aeroelasticity, the interaction of aerodynamic forces and structural flexibility, potentially causing flutter, divergence, etc. Avionics, the design and programming of computer systems on board an aircraft or spacecraft and the simulation of systems. Software, the specification, design, development, test, and implementation of computer software for aerospace applications, including flight software, ground control software, test and AMP, evaluation software, etc. Risk and reliability, the study of risk and reliability assessment techniques and the mathematics involved in the quantitative methods. Noise control, the study of the mechanics of sound transfer. Aeroacoustics, the study of noise generation via either turbulent fluid motion or aerodynamic forces interacting with surfaces. Flight test, designing and executing flight test programs in order to gather and analyze performance and handling qualities data in order to determine if an aircraft meets its design and performance goals and certification requirements. The basis of most of these elements lies in theoretical physics, such as fluid dynamics for aerodynamics or the equations of motion for flight dynamics. There is also a large empirical component. Historically, this empirical component was derived from testing of scale models and prototypes, either in wind tunnels or in the free atmosphere. More recently, advances in computing have enabled the use of computational fluid dynamics to simulate the behavior of fluid, reducing time and expense spent on wind tunnel testing. Those studying hydrodynamics or hydroacoustics often obtain degrees in aerospace engineering. Additionally, aerospace engineering addresses the integration of all components that constitute an aerospace vehicle and its life cycle. Degree programs. Aerospace engineering may be studied at the advanced diploma, bachelor's, master's, and PhD levels in aerospace engineering departments at many universities and in mechanical engineering departments at others. A few departments offer degrees in space-focused astronautical engineering. Some institutions differentiate between aeronautical and astronautical engineering. Graduate degrees are offered in advanced specialty areas for the aerospace industry. A background in chemistry, physics, computer science and mathematics is important for students pursuing an aerospace engineering degree. In popular culture, the term rocket scientist is sometimes used to describe a person of great intelligence, since rocket science is seen as a practice requiring great mental ability, especially technical and mathematical ability. The term is used ironically in the expression "it's not rocket science" to indicate that a task is simple. Strictly speaking, the use of science in rocket science is a misnomer, since science is about understanding the origins, nature, and behavior of the universe. Engineering is about using scientific and engineering principles to solve problems and develop new technology. However, the media and the public often use science and engineering as synonyms.